Hello, this is another video as part of the video series on current electricity. So in this video, we are going to discuss series and parallel circuits. So let's get to it. So first, we'll look at connections of cells, like cells in series and parallel. Series and parallel. So when you have cells that are connected in series, how do you determine the effective EMF of the cell? That is the total EMF of the cell. So let's say you have, first let's look at series. They're in series when like this. So pay attention. You have the positive terminal, negative terminal. Negative is connected to positive. It's very important. You maintain that. You have positive, negative. Negative must be connected to positive, and so on. So let's say the EMF of this cell is E1, and the EMF of this cell is E2, and the EMF of this cell is E3. So the total EMF offered by this combination of cells, ET, is basically the addition of each EMF, E1 plus E2 plus E3. Now, this is the case provided there is no wrong connection. You can see positive, negative, negative is connected to positive, negative is connected to positive, and so on. But if any cell is wrongly connected, note that if one or more cells, let me put it that way, or more cells are wrongly connected, those cells offer back EMFs, and their EMFs are subtracted that is, its EMF is negative. Their EMFs, put it that way, their EMFs are negative. So for example, let's say we have, in this connection, we have one, you have the connection this way, and one of the cells is wrongly connected like that. So if this is E1, this is E2, and this is E3, the total EMF ET will be E1 plus E2 minus E3. Now you can see that negative of this is connected to negative of it. So that's a wrong connection there. So the one that is wrongly connected, which is this one, will have a negative EMF. So that's why E3 is minus here. So that's how you calculate the total. So that's for series. Then if you have parallel, we have cells in parallel. For example, you have it this way. One cell like that, then you have another cell like that, and you have another cell like that. So this only applies when the cells are of equal EMFs, the same kind of cells. So let's say 2 volt, 2 volt, 2 volt, all through. So the EMF, the total EMF will be, if this is E1 and this is E2, oh, sorry, it's the same. It has to be EE and E because it only applies when they have the same EMFs. So E total will be equal to just EMF of one of the cells. 1. The voltage is just the EMF of one of the cells. So you don't add them because they're in parallel. So how do you identify parallel connection? Don't forget, there's a node here. Let's look at 3 wires joining together. Here, there's a node, there's a node, there's a node, So that tells you that these and these are in parallel and these are in parallel. Okay. All right. So let's take some examples on that. Examples. Find the effective EMF in each case. You have to find the total EMF. That's another way of saying total EMF, effective EMF. You have this connection. So this is 1.5 volts. 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 Then the second case, you have so 2 volts, 2 volts, 2 volts. Now, how do we solve that? Now, first you need to know which one is the positive terminal and which one is the negative terminal. You know, the longer one is the positive and the shorter one is the negative. So this is positive, negative, positive, negative, positive, negative, positive, negative. Now you can see that there is no wrong connection here. It means that the total EMF will be the sum of the individual EMFs. 1.5 plus 1.5, how many? 1, 2, 3, 4, 5. Plus 1.5 plus 1.5 plus 1.5. 1, 2, 3, 4, 5. So this will give you 3 volts. This will give you 6 volts. And that will give you 7.5 volts. So that's the total EMF of the cell combination. Then for the second case, you have positive, negative, positive, negative, negative, positive. So you can see clearly that there's a wrong connection here. It means that the EMF of this will be negative. So the total EMF will be 2 plus 2 minus 2. And that will give you 2 volts. Okay, I hope that is clear. That's for cells. Now let's go to resistors in series. Resistors in series. So let's say you have something that looks like this. 3 resistors connected in series. So the resistance, this is R1, this is R2, and this is R3. So there are certain things you need to know. This is the overall, the voltmeter that measures the overall voltage. And there's a voltmeter that measures the voltage across this one, V1. And there's another voltmeter that measures the voltage across this one, V2. And there's another one that measures the voltage across this one, V3. Okay. So what are the points to note for series connection? So all these resistors, they are connected in series, but this is the overall voltage, of the circuit. So when you have resistors in series, first point you need to know is that the same current flows through them. This is the total current in the circuit. So that is I, the total current, T, is the same thing as I1, is the same thing as I2, is the same thing as I3. So for our series connection. Then another point you need to note is that the total voltage is the sum of individual voltages across the resistors. So that is V total, which is this T here, let me call it VT, is V1 plus V2 plus V3. So that means you add the voltage here plus the voltage here plus. That's how you can think about it, that this plus this plus this will give you this overall voltage. Now, based on this, we can derive the formula for the total resistance, But you know from Ohm's law that V equals IR, right? If you recall from Ohm's law. Therefore, VT will be equal to IRT, which is equal to V1 will be IR1 plus V2 will be IR2 plus V3 will be IR3. Why I use I for all of them? Because I is the same for all of them, as I've established here, that the current that flows through them is the same. So I just use I for all of them. Okay, so IRT will be, I can factorize the I out, R1 plus R2 plus R3. So I can cancel the I's then on both sides. So RT will be R1 plus R2 plus R3. So that is the formula. It means that when you have resistors in series, you just add them up. Okay, so that is how you do that. Okay, if you have more than 3 resistors, you continue to add up to Rn. Let me put it that way. Up to Rn. So I just want to generalize it. It's not limited to 3 resistors. Okay. Now let's look at resistors in parallel. Now, for resistors in parallel, you have something that looks like this. Remember, you have to identify a node, a point where 3 wires, at least 3 wires meet. So something like this. Here's a parallel connection. Then let's say you have another one here. So now here, this is the current that is flowing through the circuit, the main current. So when this current gets to this node, the current will divide. Okay? So the current that flows through each of these arms will be different. So the current that flows through this, if this is R1, this is R2, and this is R3. The current that flows through this is I1. Let me call this I1. This is I1, this is I2, and this is I3. So when this current gets here, they will recombine here. This will meet this, and they will recombine here. Everything will combine together and will still form the I here. So the I here is the same thing as the I that will form when all the currents recombine. So this will, it will divide here. Okay? Let me confuse you. Let me just assume. Now, what are the points to note? One, when you have resistors in series, different currents flow through them. And the total current is the sum of individual current through the resistor. Of individual currents through each resistor. Through each resistor. Okay. So the current is different. You can see it clearly here. But I will be I1 plus I2 plus I3. Okay, so let's keep that. Another point you need to note is that the voltage, or the total voltage, is equal to the voltage across each resistor. So the voltage is what is the same here. The current is different, the voltage is the same. But for series, the voltage is different, but the current is the same. So that's how you think about it. So what this tells you is that VT will be V1 and it will be equal to V2, will be equal to V3. So, and all of them is equal to V. Because it's the same, this voltage is this equal to this voltage is equal to this voltage, and it's equal to the voltage that this will measure. Put it that way. Okay, so that means the voltage is the same, basically, V. Now, if I use this equation here, I said I is I1 plus I2 plus I3. From Ohm's law, I know V equals IR. So if I make I the subject of the formula, I will have I equals V over R. So if I substitute this into this equation, if I substitute that into this equation, I will have V over, that will be total voltage. So this is basically the total current. Let me put it as IT. So the VT over RT will be equal to V1 over R1 plus V2 over R2 plus V3 over R3. But we've established that all these V's are the same. So I can put V for all of them. V over R1, V over R2, plus V over R3. Then I can pull out the V. I can factorize the V out. 1 over R2 plus 1 over R3. Then V over RT. So here I can divide both sides by V so that I can cancel this V. This one too becomes 1. Then I'll have 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So this is the formula for resistance in parallel. So we'll stop there and I'll see you in the next video. Bye-bye.